Good day, everyone. My name is David Williams, Executive Director of the United States Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled NREL's Public Available Energy and Economic Modeling Tools. We are grateful to our presenter, Maxwell Brown from the National Renewable Energy Laboratory, for today's timely discussion. First, a little bit about the United States Association for Energy Economics. We are the largest affiliate of the International Association for Energy Economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services that you can find at our website at www.usae.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speaker. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our speaker, please click the Q&A button at the bottom of your Zoom window and type your question. We've allocated sufficient time at the end of this webinar to address your questions. And now I'd like to introduce you to our speaker, Dr. Maxwell Brown, Senior Energy Systems Modeler in the Economics and Forecasting Group at NREL. Max, over to you.
Awesome. Thank you, David. I'm going to share my screen. So, Rebecca, are we good? Can you see?
Perfect.
Awesome. Thank you. So my name is Maxwell Brown. I appreciate this opportunity from USAE. And as David mentioned, I'm a senior energy system modeler with the Economics and Forecasting Group at the National Renewable Energy Laboratory. And I also teach classes over at the Colorado School of Mines on computational economics and mineral energy and economic modeling. Today I'm talking about NREL's publicly available energy and economic modeling tools. And to jump into it, we have mainly I'm covering 2 models in more detail. So I'm covering REEDS, which is an electricity capacity expansion model. And I'll spend a majority of time covering REEDS, and then we'll slide into SLIDE, which is a computable general equilibrium model. And these are 2 models that I've worked more closely on. And then we'll hop into several other NREL models covered briefly, and then go into Q&A. I'll mention here, this is not all of NREL's publicly available models. The title is a little bit misleading, but it's a little better than saying some of NREL's publicly available energy and economic modeling tools. So just going right into REEDS. REEDS is the Regional Energy Deployment System. And really it takes a lot of people to develop such a model. And over time, it's been around for a long time. I'll talk about that soon. But it takes several people to manage the model, build the model, and make the model what it is today. And I'll talk a lot today about REEDS, but it's good to remember that it took a lot of people to get REEDS to where it is, and just give credit to everybody that's working on the model today. So what does REEDS do? Well, in the very broadest of sense, REED takes a set of inputs assumptions, capacity costs, fuel costs, technology performance characteristics, all these sorts of things, and it simulates how the electricity sector of the United States, Canada, and Mexico will evolve over time. And so we can think of, we start today, as of 2020, we have an existing fleet, and some of those plants will die off by 2050, and load is also going to grow. And so what replaces those units, and how do they operate? And that's really what REEDS is useful for. A bit of background here. So REEDS is NREL's flagship electricity capacity expansion model. It's been around since 2003, making it 17 years old now. And it started as WINS, which was the Wind Energy National Deployment System. And it became REEDS in 2009 after the people working on it then had added PV, photovoltaic or PV technologies. They added CSP technologies, geothermal technology. So it wasn't just about wind deployment then. It was about the bulk power system. It was about every single technology you can think of that was going into REEDS at that point. It's a linear program, and its objective is to minimize cost of operation investments. So we can think of, I mentioned earlier, how do we choose which plants will replace those that die off? But we can also think of how do those plants actually operate, and given those operation characteristics, which plants would you invest in? So when you boil it down, it becomes a very simple linear program. Just it has two components, one of investment, one of operations, and you're minimizing those total costs. And the special sauce of reads, what I like to call the special sauce, is this detailed characterization of variable renewable energy, and it does this in a few different ways. The first is we have modules that are that provide detailed representation of the capacity credit curtailment of these VRE technologies, and I'll talk about those in a little bit. But mainly, it's providing a much finer detail of the resolution that's possible for their operations and informing that into the investment decisions. And the other portion is, it is the regional energy deployment system, and we call it that because it has one of the highest regional resolutions of models in this class. And so we can look at this map here, and each of these colored area represents a balancing area. There's 205 of those within the North American representation, meaning the energy supply and demand must be met at these regions. And if you look closer, you can see smaller subregions, and that's where we can build renewable energy technologies with their own unique characteristics, with their own spur-line costs, a very detailed and rich set of information at those subregions that give us a better representation of VRE technologies. So there's 205 balancing areas with the North American version, and then 454 wind and CSP resource regions, meaning there's a great amount of detail underlying the regional and spatial resolution here. Our major constraints are just that energy supply must equal demand. This is a pretty simple one, where you have the domestic generation plus net transmission must equal the load for electricity. And then we go into operating reserves, which is, they're really a proxy for the operating reserves that are required by specific utilities, but it's mainly that you need to reserve some capacity for the as a percentage of load, PV and wind, and as well as PV and wind generation. And the biggest thing there is they become proxies for reliability, in that they control for the uncertainty surrounding these sorts of technologies. The next is a planning reserve margin, which is essentially to say that there is the amount of capacity available during peak net load hours must be equal to some percentage plus peak demand, meaning I need to have enough capacity on the grid just to meet that sort of peak demand. One of the things we pride ourselves on is the federal and state policy representation. So anything that's on the books usually gets incorporated into REIS really quickly. And in that sense, we have RPS constraints, we have RGGI, we have California's SB 100, 45Q, all these different federal and state policies are included within the model. The last thing, which we've just added, and I have a little bit more information on this later, is the climate and water constraints. And so we ask ourselves, how would the electricity grid respond to different weather patterns, different temperature changes, those sorts of things? But also, what are the withdrawal and consumption rates associated with the electric power sector? So how much water are they consuming? How much water are they withdrawing? And how much availability of that water is available in the future? So, and then finally, the last couple points we've used in several seminal studies. So REIS has over 100 publications associated with it, several more this year, and it's been used in a lot of, studies that have informed policy on different state and federal levels. In 2013, we expanded to Canada, and in 2017, we expanded to Mexico, just including these, getting a North American representation allowed us to relax some of these border conditions that we have on the north and south sides of the country. And one thing to note there is, I was just involved in the 34th Energy Modeling Forum, where we got a bunch of different modeling teams together to model the evolution of the North American power sectors and the integration of those sectors across borders. And there's a lot of interesting papers coming out, or that have come out recently from that study. So keep a lookout for those. And then I've been working closely with May Wan at MIT to link REIS with US REP, which is MIT's model of the US and global economies. So in that sense, and I'll talk about this more a bit with slide, is that we're trying to capture, some of the greater economic impacts of power sector changes, but typically in CGE models, we don't have this detailed representation of the power sector available to us. And so we take reads to supplement that, and we get US REopt to feed back, the fuel price changes, the capital and labor indices, those sorts of things. And it gives us this kind of holistic picture of what happens with electricity policy. How does that impact, the fleet of electricity and its generating characteristics? And then how does that impact welfare and, distributional impacts, trade, those sorts of things? And it gives us a very wide lens to look at these different problems. And then finally, in 2018, Amy Rose and Ilya Chernikovsky led this. I helped, but they really led this effort to put out REIDs in India, and it was very much a good proof of concept, because as I'll talk about in the next slide, I had done a lot of work to rewrite REIDs when I first started at NREL, and we made it this very general structure, such that if you were to replace the data, you could maintain a lot of the constraints and get a totally new representation. In this case, we had to add some constraints, remove some of them. But for the most part, the core structure of REIDs remained intact, but we supplemented some of the data with that from India, and we were able to get a representation of India in our version of REIDs, and that is publicly available too. So I'll talk here just on in 2000, so as a small bit of history, in 2017, I started at NREL, and myself, Kelly Urich, and David Beelan were tasked with rewriting REIDs. And so this model had been around for 17 years. Well, I guess at that point it had been around for 14 years, and there were a lot of people working on it, and they said, okay, here you go, rewrite this whole thing from scratch. And we did it, and I think we did it pretty well. There's still some kinks we have to work out, but that'll be, some of those have been fixed in the next release. But what we did when we did that was we added a lot of features. And the first one seems a little, it seems simple, but we're able to specify the years that we're going to represent. We can specify, I want to model 2010, 2015, 2020. I want to model 2020, 2030. I could model every year in between there, but it just gives you the ability to go into a CSV file, add the years that you want to model, and you can go from that. So the next point is actually something I worked on specifically, where you have user-specified technology resolution. And what we're able to do there is we're able to scale the model from having every single power generating unit in the United States represented, or having all of those aggregated into one kind of representative plant, or anything in between, really. I came up with this clustering algorithm to essentially bin plants based on their characteristics, either bin them or aggregate them all up, or keep them all at the unit level. But it gives us this ability to scale up the resolution to have every single plant represented, or to scale it down to just have one representative plant, or everything in between. It's very useful when you start getting into these larger cases that I'll talk about soon. With that, we have explicit tracking model plant vintages. In the older version of REIDs, what we had done was we had kind of rolled everything into into some representative plant, whereas now you can explicitly track when that plant was built, how long it stays around, and you can specify, I want to stay around 60 years, 70 years, or 20 years, those sorts of things. One of the largest things, one of the main pushers for getting us to rewrite this model was we had always been stuck in this myopic world. We had always solved a single year and assuming that the operations of that year lasted for 20 years. So we had this myopic representation of the future. And what we wanted to do under this project was to make it so we could solve either keep that representation intact, have a sliding window where you essentially solve 5 years at a time, 10 years at a time, and then you move forward and fix everything behind you. And then finally, we have the intertemporal representation, which allows you to solve every year at the same time in one simulation. So in this sense, these offer great flexibility for the computing resources available to you. For example, I can run the sequential case on my laptop. I might choose to run the sliding window case on one of our work servers, and then I'll run the intertemporal case on the high performance computing cluster here at NREL. But it gives you a lot of flexibility combined with these other user specified years, the user specified technology resolution, to build the model that you want. The next point is endogenous retirements and refurbishments. In the previous version of REIDs, we had it so that you could, there was kind of inter-year representation of whether a plant would stick around or not. Whereas now it's fully embedded within the optimization with the zero profit conditions essentially dictating whether you keep a plant around or not. Significantly shortened code length, about an order of magnitude considering all the scripts and those sorts of things that were associated with it. And then finally, we have the iteration with the detailed residential demand side. I put an asterisk here, and I'll talk about that in a second. But what this really is we have a representation of the residential demand side for electricity and electricity services. And with that is this huge, rich data set. We have a pretty good model associated with it. It's well packaged, but nobody's really been using it, which is why the asterisk is there. And we have a few projects in the pipeline that'll likely use it, but for the most part, this is a good place where people or grad students or somebody can do research with a great model that's been built but hasn't been used very much yet. And so we can do all sorts of different studies. If you're interested in that, just reach out. And then finally, I put the URL at the bottom here. The model is publicly available, so you can go online. You have to register just so we can kind of know who's using the model, those sorts of things. But we mentioned it's publicly available, in this case, not open source, mainly because we require the GAM software. So there's proprietary software in there that not everybody has access to. So in this sense, we can't necessarily call it open source. We have to call it publicly available. Just in the very general sense of how does REIDS work? Well, really, we start with a base system. So in this case, we start in 2010. And we backcast everything from 2010 to 2020. And what we really do is we start the system off and we get it rolling into the direction that we expect it to be in, that we know it should be in. And then we kind of loosen up those constraints and we allow the model to choose these sorts of investment decisions, operation considerations, and transmission considerations. And it does that under several different constraints. And so I mentioned regulations. We have SB 100 represented in there. We have load, different types of power flow, and ancillary services demand. But what it's really doing is it takes that system and it moves it through time, considering all these different constraints that are associated with both the physical and environmental systems that we operate around. In the next couple slides, I'll just go through some of the key outputs. So here, when I run a case, and I get my report back, there's auto-generated reports with REIDS. The first thing I look for is these capacity and generation charts. And what these are really telling us is just all different types of generators. So this is an aggregation of all the different types of technologies that are in REIDS. So for example, land-based wind, there are 10 different classes of land-based wind. Offshore wind has 15. I think we have 48 different types of CSP, 64 different types of geothermal, all sorts of very detailed technology resolution. But in the end, what we're looking at is kind of the generation install capacity over time from some set of assumptions that drive the model behavior. And this gives us, annual generation on the left and install capacity on the right. Some other key outputs, we have capacity and generation evolution by region at high geospatial resolution. And this map, we can go back to that map that we presented earlier. I could go back to this guy, and we can actually get the generation and capacity characteristics at these levels and capacity even at these sub-levels. So it gives us, a very high resolution. This is aggregated a bit because we grabbed this from a recent study. But for the most part, we can get this sort of information is available at that high resolution that we've seen before. Next is one of the useful things that we use REIDS for is the impacts of policies on clean energy deployment or any sort of energy technology deployment. And so here we're looking just in a very simple case, what happens if we extend these tax credits, the production tax credit for wind technologies and the investment tax credit for solar technologies. What happens if we extend those? And what's the combination of that with low and high natural gas prices? And so in this case, we can see this dotted line is no extension. And with extension, under the low gas price, we kind of see this difference, which would account for the extension of those tax credits. But that REIDS is really useful in this sense that you can take, the base, even just the core of REIDS, run it for all sorts of different scenarios, and it gives you all sorts of different information that we've already covered. So Next is we do have, for every one of those BAs, they are linked by a transmission network. And so we're able to see what is the transmission build out. And this becomes more interesting. So here we're just looking at high demand cases, low demand baselines, 80% renewable energy. But under all these different cases, we can see how many, or what's the capacity between regions of the transmission network. In that same sense, we can see how much they actually use that transmission network. So here we're looking at energy flows, and I really like this picture on the bottom because we have the reference case and then Sunshot, which, with cost savings and other sorts of mechanisms, we were able to, simulate a high PV environment by 2050. And what we see is there's a lot of power coming out of these high PV areas. You have Arizona, New Mexico down here, and they're really pushing out more energy and transmitting that to different areas of the country. So this is publicly available. I want people using this. I worked really hard on getting this out there. And I'd like to explain, just kind of what can you use this for. REIS is typically used to look at the drivers of power sector change, meaning what do fuel prices do for the fleet of operating units by 2050? How do regulations imposed on that? What would a carbon cap or a carbon tax or a rate-based standard? What are the different implications of all those different policies? And how does that impact capacity mix in the mid to long term? The model doesn't do unit commitment. It doesn't do, it's not a production cost model. It's looking more at an investor nationwide focus. And I'll talk about ways we're trying to relax some of that. We don't do AC power flow, meaning we keep a pipe flow representation in the open access version of the model. And it's not really meant for plant level decision making. We try to get the best data in there for each individual plant, but without going to, surveying plants and those sorts of things and getting honest financial answers, we can't really verify that, this is the exact FOM cost that, some plant in, Missouri is facing. So what kind of questions can the model answer? It's really meant to quantify the impacts of incentives, investments, regulations, all those sorts of things in the long term. It's a long-term planning model on a national scale. So looking at national policy, state level policy, but anything sub-state I usually discourage. And then thinking about how technologies can compete with each other. So if let's say I reduce the cost of a wind plant by 20%, how much more wind energy am I going to see? And in that sense, I like to look at this in a relative sense as opposed to an absolute sense. I'm not going to say, oh, there's 100 gigawatts of, wind energy in North Dakota in, 2050. I'm going to say there's a lot more wind energy in that region at that time because I changed something in the model. We're releasing the 2020 version very soon, within the next couple of months, and we've added a lot of updates there. I just want to make people aware of these. We have multiple storage durations, meaning before we just had battery. Battery was a technology, whereas now we have 2-hour, 4-hour, 6-hour, 8 and 10-hour batteries, and we have detailed representations of those batteries and their incentives for not just their ability to shift load, but for the actual energy arbitrage value, which I can talk about more if anybody's interested. We have updated wind supply curves. The Auger module is a huge lift. It was, if you're familiar with the current version of REIS, we had a submodule, which I call REflow, but it mainly calculated the capacity credits and curtailments of different energy technologies. And this is a vast improvement on it. A, it's a little bit faster. B, there's less package dependencies, those sorts of things. But what we're doing with this is we're having a simplified hourly dispatch. And so we run an 8760 submodule for REIS in between solve years or in between solve iterations. And that gives us all sorts of rich information on how the grid might actually operate under these certain conditions of after the investment decisions have been made. So maybe I invest in a wind plant. What does that mean for the curtailment in specific hours? And how can we get that into the model is what Auger answers. And so, and then the last thing, one of the major features of this is it calculates capacity credit for these variable renewable energy technologies using 7 years of weather and load data. So we have these incredibly rich data sets at NREL, which I'll talk about towards the end of this conversation or towards the end of this presentation. but it's able to get us, one of the most detailed representations of VRE performance using a wide range of different data to account for that uncertainty in those. Next is EFS capabilities. And what this is doing is, so EFS is the Electrification Future Study. And what it's looking at is kind of this, what if electricity is able to compete with other technologies to produce energy and electricity services? And what we look at here are different load growth scenarios. A big feature is load flexibility, so I can shift load between specific hours. And then finally, we have gas response, which is a bit vague here, but it just mainly means that we have natural gas response as on a nation as a whole, as opposed to just the electricity sector. And then finally, we have cooling water capabilities. I work closely with Stuart Cohen and Siraj Kanal, who was an intern with us and is now, I think, working for SNL. But what this does is, I mentioned it before, that we're looking at the cooling water consumption and withdrawal rates by individual units. And what we can do here is we can expand all of the different types of technologies to include, recirculating gas CT plants that draw from pond water, for example. There's a huge, I think it adds 1,000 technologies to the model of different permutations of those different cooling types and cooling water sources. And it just gives us, and each one of those regions that I mentioned earlier has its individual supply curve to address, how much would water access cost, how long can they keep it, those sorts of things. The second to last slide I'll talk about on REIDs. This is a project I've been working on we just started this over the summer. Patanan, who was an intern with me, went back to his PhD program, but Patanan Champiwat. And what we're trying to do here is we're trying to make, so I mentioned before we have 17 time slices in REIDs, and that's 4 for the 4 hours per season. We have 4 seasons, so 16 hours, plus 1 super peak hour, which is the summer peak hour. And that's been that way. The REIDs has been that way since 2003. And Dan Steinberg and I came up with the idea to say, well, let's be able to flexibly represent any sort of time scale we want. So let's, in this graph down here, I'm including an average week by season. So we have 168 hours times 4, we get, gosh, what is that? 762? Some large, extremely, vast amount of hours relative to that 17 hours. And it gives us the ability to put in chronological representation too. The beauty of this is, okay, the first thing, we recognize is that, will this model ever solve? But the nice thing is I can choose different subregions to model the 8760 or, average weeks or average months, those sorts of things, such that I don't need to increase the resolution or the dimensions of the model exponentially. I can just focus in. Maybe I just want to model, New York and New England as 8760, and the rest of the country can be 17 time slices or average weeks, those sorts of things. And it gives us a lot of power and flexibility to expand on our temporal resolution. It's something I'm really excited about. If you're interested in this, reach out, of course. But this is a project that I'm kind of excited about and working on personally. So. Finally, I just wanted to include these here. I'll be posting our slides through Rebecca and USAEE, but these are just links. And so you can get access to the GitHub repo for REIDs. We have a training video available. I led the first hour of that, and it goes through how to think about the model. It's a lot more detailed information on REIDs, going into some of the math and logic, those sorts of things. And then finally, we have documentation, just a good PDF document that, is hundreds of pages long that go into why we make these assumptions and those sorts of things. Okay. Next, we're going to talk about the Scalable Linked Dynamic Equilibrium model, or SLIDE. And I'd like to call out Caroline Hughes, who's been working closely with me on this project. She's an incredible data scientist here at NREL, and none of this would really be possible without her. So thank you, Caroline. And what is our motivation here? Well, we've always had, when I modeled this partial equilibrium representation of the energy sectors, when we model REIDs, when we model, what's called tempo, which is the transportation model, we really have these static boundary conditions about what's happening with the rest of the economy. We don't know how other sectors are going to respond to increases in natural gas prices if the natural gas price in the electricity, or natural gas consumption in the electricity sector declines. So let's say electricity sector becomes less dependent on gas, gas prices go down, what's the rebound effect from that from other sectors? And we don't really know. You know, some models get at it decently well. There's NEMS, E3 comes to mind, but you know, none of these capabilities are within NREL for sure. And then there are very few, you know, publicly available CGE models and data sets, especially when we consider those linked with energy sector models. So there's, I can't think of a linked version of a CGE model and a electricity capacity expansion model like REEDS. I can't think of one of those that's publicly available, but we're trying to make that happen. And then finally, we have perfect timing. Some of this has to do with the fact of the interests at DOE. Some of it has to deal with, you know, somebody knowing CGE being at the lab. And then the rest of it has to do with this release of a data set, the blueNOTE data set by the Wisconsin National Data Center, which I'll talk about in 3 slides. Just a bit of background. This was an internally funded project with development started just in February 2020. We've gone pretty far since then. This is built under the Scalable Integrated Infrastructure Planning Platform, which is SIIP. And so when you have SIIP and slide, that's the combination of those two. And then we're leveraging the open source blueNOTE data set, and it's written in Julia Jump. So Julia is a newer programming language, and Jump is essentially its mathematical programming layer. It's similar to GAM's model solving capabilities, but within an open source language. And the slide on the right, you know, I put together this very quick graphic where we can think about the connections between these sorts of things. And so we can iterate between slide and reads like we do with reads US rep. We can iterate with slide and tempo, which is NREL's newest transportation model, transportation sector representation. And we could also iterate between reads and PowerSimulations. So getting, you know, the finer detailed representations of the power system, communicate those results back to reads, communicate that back to the slide, and kind of get this larger scope of all of our different capabilities and representations of the different energy sectors. So our goal here is really to, I'm not going to read this, but it's really to take the very detailed representations of the power sector, of the transportation sector, of the energy sectors in general, and communicate that to the greater economy and vice versa. So, you know, how do capital and labor indices or impacts, those sorts of things, changes, impact the investment decisions in the electricity sector, and then how does that, you know, kind of reverberate through the economy? I like to mention what's in a name. So these are some of, you know, it's the Scalable Linked Dynamic Equilibrium model, but what we're trying to do here, so we make it scalable in the fact that we can scale down to, we're trying to make it scalable down to counties and up to nations. And so eventually we'll have this international representation, but maybe I want to keep a state level representation for Colorado and Wyoming, and then aggregate the rest of the country and then aggregate the rest of the world. But we're trying to make the data operations to be the best in class to kind of very quickly scale up and down, at least the geographical resolution, but as well as the sectoral resolution. So maybe I want to be able to represent the, you know, soybeans, corn, and, you know, tomato sectors, or I can aggregate that up to the agricultural sector, or aggregate it down even further. So we're trying to make this so users can come in, change the sort of representations that they want to answer the questions that they're interested in. We're linking it. So as I mentioned before, we're linking with reads, tempo, EMT/EMIS, which I'll talk about soon. And I just kind of compare this to the reads US rep functionality that we've developed already. Dynamic, so we're considering consideration of future market conditions. And what I'm trying to do here, and I think I'm pretty successful at it now, is doing the same thing that we did for reads, where we could have this, you know, recursive dynamic or myopic solve. We can have this sliding window solve, or we could also have the full intertemporal solve. And I'd like to include that into the capabilities of slide as well. As I mentioned, we're working with the blueNOTE data set. So we use the blueNOTE data set, and I wanted to give a lot of credit to the Wisconsin National Data Center. Tom Rutherford leads this initiative to develop an open source data set for economic modeling. And so it's called the National Open Source Tools for Equilibrium Analysis, where he's including not just, you know, the transformation of publicly available data to something that's usable within CGE models, but also creating several, you know, canonical models, representative models, those sorts of things that people can pick up and use quickly for their analysis. And so none of our work would really be possible, and this is what I mentioned earlier with the perfect timing, none of our work would really be possible without the Wisconsin National Data Center. So I would definitely go look at what they have to offer. It's very well packaged, very well written code. So thank you. Just our current status and next steps. So we were planning on opening the repo up yesterday, but we have a very good Julia programmer with us now who's kind of reviewing a lot of the code, and it's easy to say that we'll make this repository publicly available this week. I can include the link to that in the slides, or you can just reach out to me directly. I'm happy to answer any questions. What we're including in that are data operations, calibration exercise, as well as static and dynamic models. The dynamic model at this point is just a balanced growth representation by sector, so all sectors move forward at the same growth rate. And what I'm working on is adapting a technique that Edward Ballesteri and I put together to include some dynamic calibration of growth rates. And that's something I'm very excited about. I love, programmatic approaches to calibration. So if anybody's interested in that, I'm happy to talk further. Finally, moving forward, we're going to put in linkages with bottom-up energy sector models. We're going to look, we're going to perform an analysis of NREL's critical objectives. And some of the things we're looking at are capital vintaging, relaxing full employment, or having, better representation of employment in general. And then international representations, we're either going to take the GTAP data set or another data set to include other countries. And then finally, household disaggregation, so we can do distributional impacts like previous papers we've written. So next, other NREL tools. So I'm just going to talk briefly on other things that, I've either worked on or worked closely with the people that are doing these sorts of things. And so we'll start off with SIIP. So SIIP is one of the larger initiatives at NREL. And what we're trying to do here, so SLIDE is built under SIIP, SIIP and SLIDE. SIIP is, it's a platform for producing models, to have data-driven models put together. And you can look at this picture on the slides and see, we're kind of looking at different resolution of devices and different resolution on temporal scales, and looking at all these different sectors. And some of these white boxes is an older image that I would hope to be updated soon. I think we have water, gas, water, transportation, and electricity now, and some sort of building representation. And what we're trying to do is make it, a lot of our work is in linking and getting models to communicate with each other. And the idea behind SIIP is to make it so we can kind of do that much more seamlessly, instead of converting from one language to another, matching data sets, those sorts of things. We're able to very quickly go in, identify common fields across models, and get these models to talk to each other very quickly. So, and one of the key aspects here, it is the scalable integrated infrastructure planning model. And so we're trying to make it so we can scale up and down on regional resolution, temporal resolution, those sorts of things. The same way that we've done with REIDs and are working on with SLIDE. So one of the main accomplishments here is, SIIP has a production cost model called PowerSimulations. So there's PowerSystems and PowerSimulations. And Plexos is a publicly available, privately proprietary production cost model. Sorry, there's a lot of P's there. So Plexos is a proprietary production cost model. And what we're able to do here is, this is just a comparison of the calculation times for the exact same simulation that's being conducted. And we're able to meet the same MIP gap, the mixed integer programming gap, and significantly less time. And so if you're interested in doing detailed power analysis, I would definitely check out PowerSimulations. It's a Julia package that you can very quickly get up and running with. I titled this slide Next Steps in Capacity Expansion just because, I kind of harped on the fact that REIDs was a linear program. And with that, there's all sorts of caveats. So the first is, it's perfect competition. Everybody knows the same information, everybody's kind of cooperating together, and there's no, risk associated with it. You can adapt linear programs to do those sorts of things, but really it's not the best tool to start looking at, investor behavior, investor risk considerations, those sorts of things. And so what we're trying to do, I work closely with Bethany Frew on this project, who's leading the Electricity Markets and Investment Suite, or EMIS. And what we're trying to do here is represent individual investors, firms with heterogeneous beliefs about the future, looking at how market designs perform under uncertainty and imperfect information. So this is really looking at what if we had different markets for different products. You know, a good example is comparing ERCOT with several other regions, such that ERCOT just has, you know, an energy-only market, but several others have capacity markets, frequency markets, those sorts of things. And looking at, you know, the comparison of those two, and I have a nice image on the next slide to detail that a little bit more. But we're able to, in this case, is another tool built under SIIP, and we're able to communicate between essentially the next best, or the best production cost models that we have available to us, and communicate those results to investors as well. So at least modeled investors. And a big thing here is that we're trying to allow non-optimal investment, so production cost models, minimize cost, maximize profit, those sorts of things. But really, that doesn't play out in the real world. It never does. And so we're trying to make it so we can get this imperfect representation of time. Oh, I have the graphic on this slide. So here we're looking at if we change a market structure, here we have energy only, maybe capacity and ancillary services. But in the future, you know, especially with high RE systems, high VRE systems, we're going to be looking, you know, the budget, the balance sheets of energy utilities might look significantly different, and nobody's been looking at, you know, what I shouldn't say nobody, but very few people have been looking at what are the implications of that and how can we design markets to be more efficient. In doing so, we have to kind of compare, you know, with what we have now with these kind of, with these newer representations. And so we come up with 3 different representations here. Idealized competitive equilibrium is just, you know, perfect competition. An agent-based simulation, or we try to make it, it's not necessarily agent-based, it's more actor-based, but that's somewhere in between having, you know, exact strategic equilibrium, or, you know, an equilibrium program with equilibrium problem with equilibrium constraints. And then we have this approximate strategic equilibrium. As just a bit of background, we made it so we had this EPEC, an equilibrium problem with equilibrium constraints. And the problem there was it just never, you know, reached equilibrium, and it took a long time to solve. So we had several actors, each of them competing in their own way. But we had to also solve this submodule of electricity dispatch to get at these newer products that are available. And so what we've done is we've taken a machine learning approach to, you know, essentially approximate the power system conditions under different investment behavior. So we're writing a few different papers now on the agent-based portion, as well as the surrogate modeling approach on the approximate strategic equilibrium. So keep an eye out for those. So what REIS is for, so we'll talk a little bit about REopt now. And what REIS is for the country, REopt is essentially for specific sites. And so if I'm interested in maybe, oh, I want to build a wind plant to help my, I don't know, I don't have an army base, but to help my facility maintain, you know, either zero emission status or to potentially, you know, profit over time. And the problem with REIS is it's at such a large scale that it's difficult to pin down as specific regions at this point. But with REopt, you can really go online, you can put in different characteristics. It's got a very nice interface, and you can essentially model your own system as you see fit. But it's very much, you know, at a smaller scale than what REIS would do. Just talking about how REopt works. Well, there are several drivers. You know, you can think of these as, you know, goals, economics, utility costs, these sorts of things. But all of that gets plugged into what we're calling REopt Lite, but it's also just a API interface for REopt itself that gives you the capabilities to look at all these different facets of site level electricity systems. This is the newest model. So TEMPO, or the Transportation, Energy, and Mobility Pathway Options, is looking at a sector-wide transportation demand. It's a transportation choice model used to explore future pathways for transportation systems. It has a very broad representation of the transportation sector in the United States, household level mobility, but out of sample forecasting, and it uses time-resolved energy use to kind of get to these system outcomes and pathway options to look at the evolution of the transportation sector. I'm running out of time, but one thing I'd really like to harp on here, we have, well, not harp on, but to focus on just for a little bit. So we use REV in REIS. So REV is the Renewable Energy Potential model. And it's more of a platform. It's a huge data set that's available to you, but it gives you the ability to estimate kind of the the performance of individual sites, the cost of those sites to connect to the grid, the available amount of capacity, and even the distance to nearby transmission networks as well. So we have some example questions here. So like, what does solar and wind resource look across time and space? I have a nice slide on this on the next next slide. Looks at this in a little bit more detail. How much land is available? And then how far away is this land? If it's 100 miles or 1,000 miles from the nearest transmission network, what are the implications and costs of that? So we look at REV model diagram. We actually use this supply curve model in REIDS to get at our VRE costs that I mentioned before. So each one of those subregions that's available to build capacity on, you're able to represent the cost of that through this REV module, through the REV model. So we take, we're essentially taking a whole bunch of resource data set, billions and billions of information, combine that with the hourly weather user-defined system specifications. From that, we can get a site-based levelized cost of electricity, or LCOE. From that, we actually exclude layers. So we exclude, protected areas, urbanized areas, all sorts of, potentially if the slope of a mountain is too steep, or even a hill to build a wind turbine, we exclude that area. And then we get a supply curve model out of that. We get these nice little supply curves. In REIDS, we use them to represent spur-line costs to connect resources to the grid and the characteristics of those resources. But there's a lot of information you can use here. It's very useful. It's reasonably approachable. It's with all the information, you kind of have to dive in a little bit, but there are, Grant Buster actually presented on this at a previous USAEE webinar, but it's very powerful, it's very useful. I encourage you guys to look at any of these tools. And with that, just thank you. I appreciate this opportunity from USAEE. If you have any questions, you can reach out to me by email, or you can ask them in the chat. I can look at the chat now to see, I got one question. Yes, from Masahiro. I will definitely share today's slides. So, are there any other questions? Okay. Oh, thank you, Matthew. And if you all have questions about any of this stuff, or if you want any more information on any of these models, just reach out and let me know. I can get you connected. Oh, Paul Ivey, hello. So I'm assuming the different implications of the dynamic treatments, is that in the temporal resolution of REIDS, where we can either scale up or down the hours, or is that in the intertemporal versus the myopic representations? Oh, okay, yes. Okay, so the biggest thing that we're seeing, I have a couple slides I can share, absolutely. And I presented on these at Informs this last year, but what we see is that the policy ending or start dates are very influential in this case. So in the sense of, like, I mentioned those production tax credits earlier. If you can see those expiring, you buy it. It's the same as if I could buy a car for half off today, and I can see that offer is going to expire tomorrow. So we see, like, as these policies end, which we've seen in the real world too, around 2007 or 2008, we saw these huge buildups of wind capacity relative to the year before, mainly due to the fact that people were expecting the PTC to expire. It continued on, but if in the model we expire that production tax credit and you can see that it's expiring, there's a huge buy-up of wind. And in the same sense, if I start maybe a carbon cap in 2025, the novel investors here will build up to that, will build up to face that, instead of just immediately facing the consequences of any sort of environmental or any sort of policy or regulation. So there's very much this, having the foresight will create different pivot points in the trajectory over time. And data and model. Thank you. And Amaranth, our data and model delineated mostly. For REIDS, what we've done is up to there's a point where all data operations stop. And so if you're looking at the model, there's awrite-data.gams, and then there's binputs.gams. And after binputs, we essentially stop data operations at that point. And a lot of times I'll look at that GDX file, the GAMS data exchange file that includes all the data there. And that allows me to compare across cases. But if you're looking at the repo at V inputs, almost all of the data operations stop there. So, and then the model gets built. So that's why we were able to do the reads India model very quickly, was because all of the data operations cease at some point, and then we build out the equations and the structure of the model. So, oh, lots more. All the energy effective, Jim McMahon. Okay, so the next question is, what about integration with evolving energy efficiency technologies and demand response over time? This was, so the energy efficiency component in reads actually is, we essentially have fixed load, but we're able to adjust that load path. So load is essentially considered an input. We do have the ability to represent the energy efficiency impact in the residential sector through that residential supply side model, or residential demand side model, excuse me. And a lot of it, what we would need, which I haven't seen before, is like an energy efficiency supply curve that we could put into reads. It's easy to put in elastic demand in reads. I've done it 3-4 times now. But the problem is that we need some way to parameterize, the costs. If I have energy efficiency, I need to invest in that somehow. And it's either in the residential, commercial, industrial sectors, and we have the residential sector, reasonably well represented, but the commercial sector is not easy, but it's not terribly difficult. But then the industrial sector is still a black box to most people, and it requires an incredible amount of detail there. So I'm very interested in demand response. I think some of that is represented through these electrification future studies capabilities that we're releasing with the next version of the model, but it's something I'd be much more happy to talk about too. If you're interested in using the residential demand side, I'm happy to get you kind of set up with that. But for the most part, there have been studies using reads for energy efficiency, but it's not built in as one of the core capabilities for the model. Can you use LACE? Frederick, I want to say yes, and I've seen a similar question before. And the only issue there is I don't want to answer positively without confirming with the people that would know better. So I can get the answer to you soon. Richard Green, we do have inertia constraints in reads with the 2020 version that we'll release. We do have an inertia constraint, and that's just in the model. I can explain that more, but we have thought about adding it. We did add it. It doesn't do much because we're at such an aggregate level. We're at such a high level of representation that it's just kind of, it gets washed out versus like a production cost model or something similar to that. Open source data version. Oh, that's great. Omar, I'm happy to talk more about that. There's a few other initiatives that are somewhat similar to that, but I like the version management that you're proposing here. Oh, and Masahiro, yes, I will read each question out loud. And when you change the scales of modeling on the input, how well do so the next question is from Kenneth Walsh. And when you change the scales of modeling on the input, example, county versus state, how well do long-term models tend to agree? There isn't much of a difference. We really want the county level, we can think of the N+1 principle for, for different regional disaggregations and aggregations. And I haven't seen a huge difference in how those are represented. It depends on how the model inputs are changing and the representation of trade within and outside of a region. So I don't have a very succinct answer for that, but I'm hoping to write a paper on it soon, and I'd like to get your opinion on it before I publish that as well. If you have time, for example, read starts, increase X%. What happens with the revenues? Frederick Jouts is asking, if you have time, can you walk through a carbon price scenario in reads? For example, start at $25 per ton in 2022 and increase by X% over time. What happens with the revenues? We can either, so that's a very good question. And with standalone reads, the revenues are just assumed to go, to the government. And if we're doing any sort of like partial equilibrium welfare and like calculations with that, we can include those in as, return to citizens, those sorts of things. But what we're trying to do is with the REIDS US rep, we've published papers recently. Stuart Cohen, Justin Cairn, John Riley, and I published a paper recently that looks at what if we take that revenue and return it to reducing capital tax rates, reducing labor tax rates, right directly back to consumers. What if we want to compensate the lowest quintile of society, those sorts of things. So with the partial equilibrium representation as REIDS, we assume it's either lump sum transferred back to individuals, or we can combine it with REIDS US rep to look at the greater implications of that. So that's a very good question, something I'm really interested in. So thank you. Look forward to connecting. Yes, Amar, I appreciate it. Oh yes, Frederick, I'm seeing your question now. And the one question is from Ingela Titze, and it's, are you also working on a further integration of ecological aspects, land use, or resource use? I want to. I don't know of any initiatives under the REIDS portfolio that are doing these sorts of things. So I'd really like to. We're looking at water use. There's the ability to communicate that water use to other models that are there. So that's something we're working on and something I'd be interested in talking in more. Or if you're interested in just thinking about where we could kind of link in these sorts of things, there are outputs from REIDS of different types of emissions, different types of water use, water consumption rates, those sorts of things. So I have a question from anonymous attendee that how do these models incorporate policy parameters? These are all inputs. Some of the policy parameters we know that are on the books, so like the renewable portfolio standards or the RPS constraints, there are policies in place right now that include trajectories for their future. Things that are hypothetical at this point, like a carbon cap or a carbon tax, I tried to make it so you can include those really quickly at different levels, whichever level you'd like. So there's literally a CSV file that says, here is the carbon price, and I can put in any sort of price that I want in dollars per metric ton. And that'll go into the model if you enable the switches. So if you watch some of these instructional videos, you'll get a much better idea of how REIDS works. So. Okay, thank you all. It's good to see some familiar names on here, and I appreciate all the great comments. And if you have any more questions, you're more than welcome to reach out. Rebecca, I think that's all we have.
Great, thank you very much. USAEE wishes to thank Maxwell Brown for an outstanding webinar. This webinar will be available on USAEE's website for future download. If you're not a member of USAEE, we encourage you to join by visiting www.usaee.org. We thank you for attending, and I now officially close this webinar.